In this lecture, I will share how to derive an expression for electric potential due to a point source charge. First of all, let me define what is the meaning of electric potential. Suppose this is a source charge plus Q, and this is a point at infinite distance from this source charge. Suppose I have a point test charge plus Q naught, which is always taken as positive. Suppose I move it from infinity towards this source charge, and this is any point A. Let us suppose O is point of location of source charge, A is point of observation where electric potential is to be calculated. Means we are to find electric potential at point A. What shall we do? You move a point positive test charge Q naught from infinity to point A and note down the amount of work done during this journey. Suppose this work done comes out to be W infinity A. Suppose I represent this work done in moving from infinity to A as W infinity A. If I divide this by test charge, the ratio I get is called electric potential at point A. So we can define electric potential as amount of work done in moving a unit positive test charge from infinity to the point of observation. The condition is the value of this test charge must be very small, means limiting value of this thing as Q0 tends to 0 is called electric potential. This represents Q0 should be so small that its movement doesn't disturb the location of point source charge. So this is the definition of electric potential due to a point source charge. Now we have to solve this right hand side and find an expression for electric potential at this point. For this purpose, let me suppose there is a point P on the path from infinity to point A. At this point P, consider a very small displacement, that is dx vector, and suppose this distance of point P from the source charge is x, and the distance of point A, that is point of observation, from the source charge is r. At this point P, this test charge will experience Coulomb force from this source charge in this direction. Because both the charges are positive, it will be repelled in this direction. Let me call this force as F vector. Now I will write small amount of work done. Small amount of work done during this small displacement dx vector. Let me denote it by dw. By definition of work, it is the dot product of force vector and displacement vector. And it can be solved as a vector dot b vector as ab cos theta. In this case, angle between this vector and this vector is 180 degree. So I will write cos of 180 degree. And cos of 180 degree is minus 1. Answer is minus f dx. So this is small amount of work done during small displacement dx. In order to find total work done, I will have to integrate this equation. Before that, let me put the value of F. What is F? It is Coulomb force acting on Q naught due to this point charge. Value of F can be written as 1 upon 4 pi epsilon naught Q naught divided by x square, because distance between test charge and source charge at this location is x. So putting this value of F, I can write dw as equal to minus 1 upon 4 pi epsilon naught q naught upon x square. In addition, we have dx. So this is the value for dw. After integration of this equation, I will get total work done in moving the test charge from infinity to the point of observation A. Now let us integrate the previous equation. Integration dw equal to minus q naught upon 4 pi epsilon naught integration 1 upon x square dx. Because everything q naught, epsilon naught are constants, these can be taken out of integration. Now how to put the limits? We have to move from infinity to point A. In the starting distance from source charge, that is value of x is infinity, so lower limit will be infinity, and at the end the value of x becomes equal to r. This becomes the upper limit of integration, and on left hand side answer will be w, that is total work done, minus q naught upon 4 pi epsilon naught. Integrating, we shall get x raised to power minus 1 divided by minus 1 infinity to r. After simplifying, we can write q naught upon 4 pi epsilon naught. Inside, we have 1 upon r minus 1 upon infinity. Then w comes out to be 1 upon infinity is 0, and we are left with q naught upon 4 pi epsilon naught r. Now let's take this q naught to left hand side, and we are left with q upon 4 pi epsilon naught r. Now this left hand side is nothing but the definition of electric potential. We have calculated work done from infinity to point A. So this left hand side gives potential at point A is equal to 1 upon 4 pi epsilon naught q upon r. This is the final relation for electric potential at point of observation A due to source charge Q that is located at distance r from point of observation. It is very much clear that on the right hand side we have only scalar quantities, so electric potential is a scalar quantity. The next point I want to share is what is SI unit of electric potential. SI unit of electric potential can be defined from the definition of electric potential. It is the ratio of work to charge. Just I have defined. If work done in moving the test charge from infinity to the point of observation is 1 joule, and the magnitude of test charge is 1 coulomb, then unit of potential is known as 1 volt. So this is the SI unit of electric potential. So we can define 1 volt of electric potential as at point of observation electric potential due to a source charge is said to be 1 volt if 1 joule of work is done in moving a test charge of 1 coulomb from infinity to the point of observation. This is the definition of 1 volt of electric potential. That's all.